的监控和控制。在实验室里，我们的研究员他也会使用 ADC 来收集实验数据，比如说一些粒子物理实验、天文观测等等，还有数字示波器、数字万用表等等测量的仪器，它也需要使用到 ADC 来测量电压、电流等参数，并将结果以数字的形式进行显示。还有许多的实验室里，我们的研究员他也会使用 ADC 设备来收集实验数据，比如说一些粒子物理实验、天文观测等等，分析生物的电信号，还有数字示波器、数字万用表等等测量的仪器， ADC 的它也需要使用到 ADC 来测量电压、电流等参数，并将结果以数字的形式进行显示。来说的话，还有许多在实验室里，我们的研究员他也会使用 ADC 设备来收集实验数据，比如说一些粒子物理实验、天文观测信号分析生物的还有数字示波器、数字万用表等等测量的仪器 ，ADC 的它也需要使用到 ADC 来测量电压、电流等参数，并将结果以数字的形式进行显示。还有许多在实验室里，我们的研究员他也会使用 ADC 设备来收集实验数据，比如说一些粒子物理实验、天文观测信号分析生物的还有数字示波器、数字万用表等等测量的仪器 ，ADC 的它也需要使用到 ADC 来测量电压、电流等参数，并将结果以数字的形式。那目前来说的话，还有在实验室里，我们的研究员他也会使用 ADC 设备来收集实验数据，比如说一些粒子物理实验、天文观测信号分析生物的还有数字示波器、数字万用表等等测量的仪器 ，ADC 的它也需要使用到 ADC 的性能参数。这些性能参数包括有积分非线性、微分非线性、失调误差、增益误差等等。静态测试的方法其实已经研究了很多年了，国际上目前已经有一套标准的测试方法，它通常涉及到对 ADC 输入电压的这样一个精确控制和测量。那动态测试它的重点在于 ADC 在交流条件下的性能表现。动态测试的参数包括有总谐波失真、信噪比、无杂散动态范围、有效位等等。动态测试通常需要使用模拟信号源、时钟源、ADC 评估板以及 PC 端里的傅立叶变换的分析软件。测试方法包括有动态信号叠加测试法、直方图法等等。所以可以看出 ADC 它的性能测试其实是一个复杂并且精细的过程，需要专业的测试设备和环境来确保 ADC 芯片的性能符合特定应用的要求。理论上来看， ADC 测试其实比较简单，主要分3步。首先，我们可以把 ADC 的线引出来，然后输入端接入标准的测试电平，再在输出端进行数字信号接收就可以了。也就是说，我们至少需要模拟信号发生器和数字信号捕获器。但其实在实际工程中，测试环境还是比较复杂的，我们需要更多的设备。首先，我们需要供电的电源来为整个系统和 ADC 去进行供电。其次，我们需要提供参考的电压来用于校准，还有验证 ADC 的转换精度，然后是我们的模拟信号发生器，用于生成测试信号，包括有直流信号，还有交流信号。信号源需要能够提供精确的电压和频率以及可能的调制，来模拟我们实际应用中的信号情况。除此而外呢，我们还需要时钟源为 ADC 去提供时钟的信号，这对于同步转换的过程来说是至关重要的。时钟源需要具有低相位噪声和高稳定性，来确保 ADC 的性能不受时钟信号的质量的这样一个影响情况。那最后的话就是我们的数字信号捕获，它负责去接收我们输出的数字信号。通常我们还需要配备相应的软件系统来控制整个测试过程，以及收集数据和分析结果。所以这么看来，整个测试环境的搭建也并不是一件轻松的事情，也许有很多工程师在这个上面都很有同感。那我们解决了测试需求的问题，我们还需要去了解在进行 ADC 性能时，ADC 性能的测试的时候，通常会遇到哪些问题。我们的工程师们可以将自己在做测试时遇到的难点、痛点分享在评论区，大家一起讨论。那我们在这里要说的就是2大常见的痛点。一是为了方便测试，对于测试板的设计相当复杂，测试板需要承载更多的功能，我们需要考虑每一个板子的电源输入、时钟信号输入等等，从而去实现一整套测试。那第二个呢，就是整个测试环境它系统搭建起来其实是非常麻烦的。在硬件层面，我们的用户不需要 不仅需要自己去选仪器，而且还需要去找相互之间参数匹配、控制连接方式是合适的，而且还需要分别去控制和维护。那如果整套系统跑不起来，那还需要去逐个仪器进行排查，还有调试，找出哪里有问题，看看是不是仪器之间相互不兼容。从软件的角度上来看呢，通常我们用 ADC 性能测试的软件也需要用户自己来编程开发，去分别的对设备仪器去进行控制和分析，需要来回的调控，工程量不小，也比较麻烦。那刚刚为各位分析了 ADC 性能测试的测试需求和一些行业痛点，接下来呢，我想详细介绍我们 ADC 性能测试方案的细节，为大家介绍它可以为大家解决 ADC 性能测试的哪些难题。我们先来看看德斯特 ADC 性能测试方案它支持的测试项。我们在这方面呢，可以说是做到了 all in one， 也就是说，刚刚提到的哪些测试项，我们都是完全支持的，甚至还可以做一些 DAC 的线性测试。那我们再来看看整体方案到底怎么样。其实就像这个框架图所示，整个方案清晰又简洁，包含了做 ADC 测试所有必须的仪器，它们都模块化的集成到了整个平台上面，整体就是一个机箱，从而在硬件形式上我们也做到了 all in one。那我们再来看看整个机箱长什么样。我们为什么说它是模块化可定制的？大家可以看到，机箱由平台主控、模拟信号发生器、供电电源、数字化仪、参考电压以及包含时钟和数字信号捕获的 DIO 组成。这些模块的选择都是可以按照咱们实际的测试需求来配置的。可以看到，我们这里的槽位其实也没有用尽，一共有9个槽，因此也可以再加额外的模块来用于多通道 ADC 的测试，或者是说您可以用一套测试平台，同时去匹配多个测试项目的测试需求。那如果是 ADC 测试的话，您可以选择模拟信号发生器，加上多功能 DIO， 加上可调电压的参考源，再加上平台主控和 UUT 的供电电源就可以了。如果是 DAC 测试，那我们就把模拟信号发生器的配置换成数字化仪就行了。那如果是 ADC 测试和 DAC 测试的需求都有，那么可以选择我们整个 all in one 的全部配置组合的完整功能。那接下来我们再来详细看看每个模块。正如前面所说，用于 ADC 测试的其实主要就是这4类模块。第一个是参考电源卡，它负责提供标准的参考电平。第二个呢就是供电电源卡，它负责驱动芯片供电。第三个呢是任意波形发生器卡，它负责给 ADC 去提供采集所用的信号的。那第4个呢就是 DIO 卡，它主要用于数字信号的捕获，或者说在 DAC 的情况下作为数字源的输出。我们先来看看 AWG 模块，它是一个需求跨度比较大的模块，因此我们做了4种不同位数、采样率以及幅值范围的可选项。具体选哪款的话，我们就需要根据我们需要测的这样一个 ADC 的情况来进行匹配和选择。稍后呢，这个部分会由萨兰德的原厂的技术工程师为大家展开详细的介绍。那电源以及数字 IO 模块这边，根据我们的经验，这一种型号的可调范围就已经能覆盖绝大部分的用户需求了，因此我们没有做更多的可选的型号。但是这个模块其实它本身就是可选的，可以根据客户的需求来进行选择。那刚刚我们还有提到说，还需要有控制整个系统和进行结果分析的软件，我们就刚好搭配了这样一个相应的免费的配套的软件。我们会以光驱或者文件的形式来提供上位机的软件。这里可以看到，对于每一个模块，我们都可以进行相应的设置和控制。那同时呢，我们也提供配置在机箱中的这样一个下位机软件，方便大家直接的简易的去进行操作。它是通过背板来相互触发的。那我们再来看看软件的分析部分。在结果视图中，除了右边能够直接给出我们所需要的测试结论而外呢，或者是说除了提供写进我们 datasheet 的各种参数结果而外，那左边我们还可以给出丰富多样的各种视图，来方便工程师做更深一步的分析，例如静态分析、频域分析、统计分析等等。所以总结下来，我们整个 ADC 的性能测试方案，它能为用户带来的价值，其实主要体现在这3点上面。第一个呢，就是高度集成。 整个方案它提供模块化的选择，可以支持我们的用户去定制化的自由搭配各种各样的产品，并且我们多项参数都是可调配的，也就是说可以适配于每位用户的需求。那不管你有哪几种测试的项目，哪几种测试的方案，多项的测试内容，一部系统就可以去搞定，而无需去额外的进行采购，从而也降低了我们这样一个整体的成本。第二个呢，就是整个方案它其实是开箱即用的，我们的方案中它内置了软件，也方便您去统一的去管理硬件，或者说对于整个测试流程进行把控，按需去进行配置就可以了，我们拿到手就可以直接启用。而且它是自动的去联动来触发采集的，无需工程师们自己去搭建软件平台来适配各方的硬件产品。第三个呢，就是所得即所需，我们提供的高精度硬件搭配了内置的这样一个校准，所以说可以保障测试的准确有效。同时呢，我们每个模块它所得的数据会自动的去通过配套的软件来分析和处理，直接给出关键的结论，无需工程师们去开发额外的程序来进行补偿、汇总、运算，也方便各位工程师去直接的上手使用。那我们来看看之前谈到的2大行业痛点，在这个方面，在这个整个方案中呢，有没有得到解决？那首先呢，就是测试板设计的难度和复杂的问题。因为我们的系统呢，集中的去集成了供电的电源、DIO、时钟等模块，所以说测试板的设计也不再需要考虑这些的功能，从而大幅的简化了测试板的设计，可以说是简化工作，不减结果。那再来看看整个测试环境的搭建，因为我们在硬件内部也做好了联调的控制，它们之间不存在兼容性的问题了，所以说是可以轻松的去搭建我们的测试环境的，您的工作桌面也可以更加简洁，更加舒适。好了，那现在大家对我们的 ADC 性能测试方案也有了基本的了解，那再来看看我们有哪些典型的场景，也可以让大家更深入的去感受到我们 ADC 性能测试方案的强大。首先，我们以这个斜坡测试为例，看一下整个这套系统它是怎么完成一个静态测试的。那首先，我们用 AWG 模拟信号发生器来输出精确的斜坡信号的模拟信号源，再由 UUT 的参考电压去转换为数字信号，再由我们的 DIO 去进行捕获，输出测试电压。整个这个过程中时序都是可以配置的。然后我们会对这个过程进行循环测试，汇总出每次测量的测试的这样一个数据，从而分析跳变点，找出每个扣的所对应的电压，然后根据对应电压值来做运算、绘图，包括计算每个转换台阶的 DNL 和整个转换范围内的 INL 等等。最终的话，我们会根据分析的结果来生成测试报告。整个过程其实都是自动完成的，不需要您单独的去进行编程，所以说整个流程是非常清晰和便捷的。那目前全球范围内的话，有很多知名厂商已经是我们的客户了，可以说我们的方案遍布了全球，包括了半导体行业的龙头 NXP、ADI、TI、英飞凌、意法等等，其实这些都是我们的客户了。首先的话，我们再来看看第一种的应用场景。那针对于那些专门集成设备制造商，还有一些应用特定集成电路的供应商，去提供研发服务的团队来说，他们会需要针对专门的 ADC 芯片去进行性能分析，包括可能调整各种各样的参数，所以说这通常需要用到一大堆专门的仪器和设备来一起进行调试和控制。那在这个方案中，我们的客户就选择了使用德斯特的 ATX 平台模块来升级他们的测试系统。在这个新的方案里面，使用了德斯特的 ADC 性能测试的整个方案，其中所用的 DPS、DIO 模块替代了以前用的那些独立的台式设备，而且这个平台它自带的自动化测试软件 ATVU 可以去控制所有的模块，包括说电源、数字 I/O、TPS、AWG 等等。这样一来，不仅搭建测试环境变得更简单了，工程师们用起来也更方便，控制也更顺手了。那我们常见的第二个场景就是面向于微控制器单元和系统性芯片设计公司以及应用集成型用户，针对于 MCU 集成了 ADC 的这样一个场景下，需要对 ADC 进行测试、验证或者出厂检验的环节来提供帮助。那针对于 MCU 集成了 ADC 的场景， 会比前面我们测专用的 ADC 芯片会更复杂一些。因为 MCU 中的 ADC 它通常是需要跟系统中的其他组件，比如说 CPU、内存、外围设备等等去集成到一起，而且测试的时候，我们是一般来说不能去直接的访问 ADC 的内部信号，所以我们会进行相应的处理。那稍后我会详细的展开介绍怎么去处理它。那在这里的这个测试环节中呢，我们的核心配置依然是采用了德斯特的 ATX 测试平台，然后利用德斯特的 ATX 系统中的 AWG 模块去产生激励的信号，再用 DIO 模块来采集输出。在这里也是有平台中的自动化测试软件 ATVU 来控制所有的模块，包括电源、数字 I/O、DPS、AWG， 所以说整体来说是非常方便的。那说回如何解决 MCU 集成 ADC 的场景，我们通常采用2种方法来进行测试。一个呢是直连芯片内的硬件调试总线来获取数据，那这种方法通常涉及到硬件调试接口来直接访问 MCU 内部的 ADC 模块。首先，我们可以使用支持相应调试接口的这样一个调试器，例如 GTAG 调试器，来连接到 MCU 的调试端口。那通过调试器，我们可以读取和写入 MCU 内部的集存器，包括有 ADC 的控制和状态的集存器。然后我们可以通过调试器来设置 ADC 的参数，比如说它的采样率、参考电压、分辨率等等。然后我们可以通过启动 ADC 的转换，就可以通过调试器来直接的读取我们的转换结果了。最后，我们可以将获取的数据传输到 PC 端上的分析软件中，来进一步的进行性能分析。那这种方法的话，可以去直接的获取 ADC 的原始数据，不需要 MCU 的 CPU 来参与，因此可以更加准确的去评估 ADC 的性能。那第二个方法呢，就是编写固件，使我们的 MCU 整个的去等效成一颗 ADC。那首先我们需要编写固件代码来配置 ADC 模块，控制整个转换的过程，并将转换结果通过 MCU 的通信接口，比如说 UART 等等来输出，再将我们编写好的固件烧入到 MCU 中，然后通过 ATX 的测试平台的 DIO 模块连接到 MCU 的 GPIO 口，通过发送控制命令到 MCU 来启动 ADC 转换，并且可以通过 GPIO 口去接收我们的转换结果。那最后呢，我们可以使用 ATVU 软件对收集到的数据来进行处理和分析，评估我们 ADC 的这样一个整个性能。这种方法它的优势其实在于它可以模拟 ADC 在实际应用中的工作情况，包括 MCU 内部它可能会对 ADC 性能产生的影响，可能有各种各样的因素，但是它可能需要更复杂的测试设置和更长的测试时间来得到更准确的结果。所以说2种方法其实各有优缺点，选择哪种方法取决于我们工程师他的测试目的，或者说测试的这样一个资源的掌握情况以及设备的可用性。在实际应用中，可能需要结合去使用2种方法来获得最全面的 ADC 的性能评估。好的，以上呢就是我今天分享内容。首先给大家分析了一下 ADC 性能测试方案它有哪些应用场景，有哪些行业痛点。那么第二呢，就是再为大家详解了一些我们德斯特 ADC 性能测试方案的组成和它为用户带来的价值。最后呢，向大家分享了一些典型的场景。那么下一场呢，我们邀请了来自萨兰德的半导体行业专家来分享产品具体的用法和一些实际的应用案例。大家有什么问题和关注点，可以发在评论区，我们会在第2场萨兰德的专家进行分享结束过后来一一解答。如果大家对我们的 ADC 性能测试方案感兴趣的话，可以加入我们的交流群，与我们的工程师多多交流，来获取更多的资源。好的，非常感谢大家，让我们有请主讲人来拉回现场。
好的，非常感谢赵工的一个分享和讲解。赵工今天呢为我们详细分析了 ADC 性能测试方案和应用的场景、测试需求、行业痛点等等。并且呢，根据这些挑战和难点，带来了一套高度集成化、定制化、简便化的焦钥匙 ADC 测试解决方案，并且呢，通过2个案例专用的 ADC 芯片测试以及 MCU 集成 ADC 测试呢，这2个案例让我们对方案有了更深入的了解。 那也正如赵工所说，目前这套测试方案已经为恩智浦、高通、意法半导体、飞利浦等诸多国内外的知名客户提供了方案与测试手段，那也提供了良好的应用与长期效益。那再次感谢赵工的一个分享，那请赵工稍事休息。那我们看到评论区有一些问题，这些问题将在我们第2场演讲结束之后呢，由Thailand的技术专家为大家做一个详细的解答。好的，那请赵工稍事休息一下。接下来呢，我们将继续深入探讨 ADC 以及 DAC 测试的技术细节。为了确保 ADC 和 DAC 设备的性能和可靠性呢，我们采用了一系列严格的测试方案和先进的一个测试设备。我们本次邀请到了来自 Thailand 的专家。那 Thailand Engineering 是一家国际领先的测试技术和工程公司。自1992年开始呢，他们就专注于为全球的各个半导体行业去提供解决方案和服务，帮助半导体制造商提高测试效率和质量。那 Host 和 Ewan 是荷兰 Thailand 的销售经理和技术专家，他们负责模拟测试解决方案已经有超过25年的经验，可以说是非常的精通这一行业了。所以呢，那接下来在这次演讲中，我们将邀请到他俩来为我们分享这个 ATX 7006A 高端 ADC 测试系统的一些方案和它的一些构成，并且为我们讲解如何通过这些组件实现 ADC 以及 DAC 的测试。那下来，让我们欢迎 Host 和 Ewan 为我们带来分享使用 ATX 7006A 高端集成系统进行 ADC 与 DAC 芯片的一个精确测试。
Can we start? Yeah?
Yeah.
Okay.
So we are very happy to have Horst, Ivan, and Tianru from Thailand Engineering here today. Now we can get started and see their insights of semiconductor test field. Yeah, you may get started.
Good afternoon, everybody. Thank you for joining this session. My name is Horst Beekhuizen. I'm going to show a presentation about measuring AD and DA converters with our Applicos ATX 7006A, our test lab in a box. Today's presenters are, beside myself, Ivan Boersma. He's a senior engineer and an expert on the ATX. And Tianru Chao, she's also an engineer and a Chinese colleague who can do some additional explanations in Chinese upon your questions. So continuing, one moment. Here we go. I want to start with a short company introduction. Thailand Engineering is a company that has existed for over 30 years now. Recently, we have been acquired by Advantest Group. Advantest is a multinational company with over 3,500 employees and specializing in ATE. Thailand Engineering is a company located in the Netherlands, and we specialize both in ATE, so automatic test equipment, and bench test solutions, for which we are here today. Thailand has over 95 employees. The majority of this is our engineers, and we specialize in a number of fields. So to the left, you see test application solutions. Here we translate a datasheet into test application software. This is the software that tells the big testers how to test a device under test. These are usually production testers. And besides the software, the test application software, we also developed the test application hardware. These are the load boards or the device interface boards, which connects the device under test with the instruments in the tester. The second part of our expertise is production test. We have the largest independent production test floor in Europe that consists of Teradyne handlers and testers, 93K from Advantest, and a lot more. We also have partnerships with these vendors, so with Teradyne and Advantest and other companies, for whom we develop instruments. So we develop these instruments for them, and they take them into production themselves, but we also produce them in small batches for them. This brings me to the fourth part, our in-house manufacturing capability. So for some instrument production, but also for our own products, we do final assembly and final test in-house. We also provide calibration services for our products. So for example, for the ATX. So last but not least, for which we are here today, our PXI and bench test equipment that we completely develop in-house. So for example, the ATX for which we are here today is completely developed in-house. This is our customer base worldwide. You probably see some familiar names here. And we provide also support to these customers, either directly or through our representatives, like Tesat, who is one of our valued representatives. If there are any questions this far about our company, you can ask them. I'll wait a second, and otherwise I will continue. Good. If there are no questions, I will continue with the presentation. So the ATX 7006A is a complete test lab in a box. By this I mean this chassis contains all the instruments that you will need to develop, to measure on a AD converter or a DA converter. It can contain a combination of instruments which are necessary to perform these measurements, and the system also is able to perform all the necessary calculations. So taking a closer look, you see the system here before you, and to the left you see the controller, and in the rest of the chassis are the various modules. This system is intended for both static testing and dynamic testing. So static testing or linearity testing consists of performing measurements that leads to calculating parameters like INL, DNL, etc. And dynamic testing allows you to calculate values for SNR, so signal to noise ratio, THD, total harmonic distortion, and so on and so forth. So everything is possible within this one system. Oh, sorry, too quick. Here you see again a description of what I've just described. So the linearity testing, dynamic testing, which you can do for both AD converters and DA converters. So here you see some use cases represented. To the left and the middle, you see test setups with the ATX for testing ADCs in a microcontroller. These are setups from our customers, or from two of our customers actually. And to the right you see another example. So the first two examples were for integrated device manufacturers, so large companies that develop integrated circuits and also take them into production. And the company to the right is an example of an institute whom also use the ATX. Universities do that also, by the way. In this case, it's the Swiss World Radiation Center. They specialize in solutions for measuring solar radiation in space. And they use the ATX to validate AD converters and DA converters, which will be utilized in solutions that go up in space with satellites. So these are basically the kind of companies that use the ATX. We see that typically at semiconductor development companies, institutes, and universities. Sorry. Taking a closer look at the ATX, you see to the left here the picture of the controller module. It runs on Windows. It has an embedded PC inside, and you can connect to the ATX via either GPIB, Ethernet, and USB. The controller module, by the way, is also able to perform all the calculations. So you can do that externally via a PC, or you can do that with the controller itself. The modules that we deliver, these are also completely developed in-house. Everything, so from the chassis up to the modules, are designed for extremely low noise. So the ATX does not use a bus standard such as PXI, but it's a proprietary bus standard and completely designed to enable the lowest noise level possible. This is also true for our modules, beginning with the arbitrary waveform generators. Here you see two examples of high resolution modules, in this case 22-bit and 20-bit, sorry. And this slide shows the two high-speed modules that we have in our range, so an 18-bit and a 16-bit version with up to 400 megasample update rate. These modules, so the generators, are typically used for measuring on an AD converter. If you have a DA converter, then you would need a digitizer module or multiple digital digitizer modules. In this case, we have 3 variants, so 2 high resolutions version and 1 high speed version. Going through the final 3 modules that we have. So you've seen the generators and the digitizers, but for measuring on an ADC or a DUC, you would also need a reference source. This is the module to the left, which is a 20-bit DC source, and it is used for both as a reference source for the converter as well as for the ATX itself. So internally. In the middle, you see our dual channel low noise, again, power supply you can add to a configuration, and digital I/O for low jitter clock and source and capture capability. It's also able to generate patterns that you can program yourself. So this concludes the hardware part. I hope I'm not moving too fast. If you have any questions, I will wait a minute and then continue again. I can continue? Yeah, okay. All right. So the ATX is always delivered with software. The software consists of 2 parts. The first one is the control software which you see here. ATView 7006 controls the ATX. The screenshot of the GUI you see here represents the modules that are used. So the modules that you have in your configuration are represented here as window panes, and each pane represents a module. Here you can set all the parameters that are necessary to perform the measurements for your typical converter. And if you have done so, then you simply press start. The system will perform the measurement and then automatically start the second piece of software, which is Wave Analyzer. And Wave Analyzer is gives you a visual representation of the test data, as well as the calculated values of your particular measurement. In this case, you see here a static measurement or linear measurement, and some of the values that are typical for this kind of measurement. So in this case, INL, TUE, total unadjusted error, and DNL, sorry. But that depends on your settings and on your parameters, which values it will show. On the top, you see some buttons for manipulating the data, or zooming in or zooming out of some parts of the screen. And then you can zoom in on any part and look at the values there. So if you perform a dynamic measurement, then you can, for example, have FFT, a fast Fourier transform, performed, and this will give you what you see here on the screen, a representation in the frequency domain. Here you see the carrier, the harmonics, and also the noise floor. And again, the values that are typical for these kind of measurements. So THD, SFDR, SNR, ENOP. SFDR, so for example, spurious-free dynamic range, ENOP, effective number of bits. These are all automatically calculated. So if you would like to acquire an ATX, that is of course possible. We deliver it as a complete package. When you order an ATX, it will be made to order, and then it will be calibrated and optimized before shipment. And in the shipment itself, you will find the software, all the required documentation, cables, as well as a demo board. I have a slide on the demo boards and the accessories later. But if you order a certain configuration, then you will also receive an associated demo board, and this will allow you to already perform measurements and get acquainted with the system without directly connecting to your actual device under test. Oh, sorry, a bit too fast. So here you see examples of the demo boards that we can deliver for you, and you can also order them additionally if you would like, would like to have more than one. We also deliver breakout boards, so a conversion of, in this case, from LIMO to BNC, but we can deliver variations of that as well. So now we come almost to the conclusion of this part of the presentation. My colleague Iwan will show you live a measurement with the ATX. We will do that with one of our demo boards. Here you see how the AD converter in this case is connected to the ATX and which modules there are utilized. So two generators, the reference source, the power supply, and the DO are in this case utilized and connected to the AD converter. And the demo board in question is our AD7671 demo board. So a demo board based on the analog devices 7671 SAR ADC. Here you see an overview of the chip in question. This is what the setup will look like. As you can see, there's no other equipment really necessary around the ATX. Typically on the bench you would see power supplies, scope, and other pieces of equipment. Here it's completely integrated in the ATX. So here are some specifications of the demo board itself, of the chip itself. As you can see, it's a 16-bit converter, 2.5 volt reference source, 5 volt power, and connected to the ATX. This concludes my part of the presentation. Thank you very much for listening. I will now move out of the presentation mode and transfer to my colleague Ivan. Thank you again.
Good afternoon, everyone. Welcome at this presentation or at this demonstration with the ATX 7006 tester system. Can everyone see my screen?
Oh, ik heb alles net zacht gezet.
Okay, thank you. On the left side, I started, you can see the software AT view and the different panels for the module configurations. I will shortly discuss some of the panels. Here on top, you see a general panel configuration for the device under test. So here we say we are testing a 16-bit ADC device with minimum input voltage of minus 5.5 volts and a maximum voltage of 5 volts. We are using our 20 bits generator in the ATX system as a signal source, and we capture the data with our low-speed digital I/O module. Here on the panel below this general panel, we see the configuration for the digital I/O module. The device under test is a serial ADC. It's working at 3.3 volt levels, and as we mentioned before, it is a 16-bit device, so the serial length of the data is 16 bits. We are using the AWG22 as a signal source, so it takes over the configuration for the capture memory from the digital from the generator module. The generator module we see on the one panel below the digital I/O module. Here we configure a sine wave to get started, a sine wave signal with a frequency of about 1 kilohertz. And an amplitude level of about 5 volts, a little bit below 5 volts. The device also needs, the board also needs a power supply of 5 volts. So that's what we configure on the power supply module panel, and the reference voltage is 2.5 volts. So if we go back to the diagram of the demo board, here we see the power supply that is connected to 5 volts. It's connected to the device on the test and programmed at 5 volts. The reference voltage is also connected to the ADC and programmed at 2.5 volts. The AWG module is connected to the input, and there is some possibility to change the analog input ranging with some relays on the board. And the relays are connected to some programmable static bits that are connected to our digital I/O module. That's what we can find here on the panel. Here we have static output bits, and we can programming them 1 or 0. We did programming at all at 0, meaning that static bit 0 and 1 are 0. That means that we static bit 2 and 3, sorry for the ranging. That means that we have a range from -volt to +5 volt. The digital signals are connected to the digital I/O module, so the serial clock, the conversion start, and the chip selects are connected to the digital I/O module and controlled using the pattern bits. The pattern bits can be found here, and here we find how the pattern bits will start conversion for the device on the test. So here we start a conversion. Then when the conversion is ready, we shift out these bits and shift out these bits serial into the digital I/O module. I think that's in short what the configuration is. So now we can run a measurement. If I press the start button on the generic panel, it will send the configuration to the ATX controller module, which configures every module in the system and then starts a test. And after the test, it collecting the data, and here, when the data is received by us on the PC, we can see the results, and here we see our sine wave captured with our digital I/O module. You can zoom in a little bit more, and we can see the steps. As you can see, this signal can be analyzed using the fast Fourier transformation. So if we press the fast Fourier transformation button on the top, the data is transformed to a frequency spectrum, as you can see here. So on the x-axis, you see the frequency. On the y-axis, you see the amplitude. And here we have our carrier on the left side. And this one is approximately 1 kilohertz, as we did program on the AWG panel. And here we see our calculations. So we have calculated the total harmonic distortion and showing each harmonic that's being used for the calculation of the total harmonic distortion. We show our spurious-free dynamic range, so the maximum peak besides the carrier, the spurious noise, which one is the highest noise and which one is the highest harmonic. We calculate the signal-to-noise ratio, the signal-to-noise ratio including the distortion, and we calculate the effective number of bits for this device. When we apply a second tone, it will also perform IMD calculations, intermodular distortion calculations. But in this case, we only apply one input signal with one frequency, and we do not have this kind of calculations available. So this is the easiest way to test a dynamic test with this demo board. Are there any questions about this setup, this measurement? No questions? No further questions?
Yes, Ivan, so far we do not have further questions. We can continue. And actually, we got several other questions, and we will deal with these questions in the end of the presentation and demonstration. Thank you.
One moment. I will do another part of the demonstration, and then we can continue with the question and answers.
Yeah, thank you.
A big advantage of the ATX system is that you can do dynamic measurements and static measurements with the same setup. So when I want to do the static measurements, I change my input signal to a ramp. I program a ramp voltage of -5 volts to +5 volts, a little bit above and below, so that we can detect the offset and gain error. And we apply just one ramp to the input of the device. We run the test again. We wait for some time. And here we have, oh, 1 moment. I haven't increased the number of samples. Since it is an ADC, we need to apply a lot of input steps to calculate the transition points for the ADC. I will start the measurement again. It will do the measurement. It will take a little bit more time because we have to do more conversions. And here we have our results. And we can calculate, for example, the best fitting or the endpoint error transition plot. Here on the right side, you see the device and the test information and the calculated error parameters like the integrated nonlinearity, the position of the worst INL value, positive and negative, the total unadjusted error. So that includes also the offset and gain error, the differential nonlinearity. So what is the biggest error in the step? Offset, gain, and mid-scale error, full-scale error. So this is the part of the demonstration, and now we have time to discuss some questions from your side. Thank you for watching this.
Yeah, so thank you all for the insightful presentation and the vivid demonstration, and which has aroused much interest from the audience, and we got many questions, and we have selected some of the most frequently used asked ones. And Tianru, could you help me to translate them?
Yes, no problem.
There seems to be an echo here.那第一个问题呢是 ATX 7006能够作为 PSRR 测试吗？怎么用这个系统去做 PSRR 测试呢？
Is the ATX can do the PSRR test, and how to do the PSRR test?
For the PSR test, you can see my screen.
作为这个 PSR 测试，你可以看到显示的界面吗？
You can use the DPS module, and one of the things you can do is to generate a signal.
你可以使用我们的 DPS 这个模块，然后你需要做的事情是勾选这个信号发生器。Yeah.
And this will apply a sine wave or a signal additional to the power supply. That's one way of doing a PSR test.
然后可以在这边去申请一个sine 波形的信号给到这个电源，这是相应的方法可以测试到这个 PSRR 值。PSRR 值。这个回答，Are you finished your answer?
I hope this part is clear enough for you how to get started with a PSRR test.
您认为这个方法的话可以回答您的问题吗？
Yes, and thank you for your answers. Because we have several answers here, several questions here, so we can move on to the next. 所以第二个问题呢是50赫兹输入能做到 ENOB 有20位吗？这种情况适合哪款 AWG 呢？
Is the 50 Hz input and to test the ENOB is possible? 可以把这个问题就是再重复一遍吗？因为我在记录一些其中的一些数据。
好的，50赫兹输入能够做到 ENOB 有20位吗？这种情况适合哪款 AWG？
the 50 Hz input can make the 20 bits ENOB test, and if in this case, which kind of AWG can be used?
I don't quite understand the question.
Yeah, they
50
mentioned.
Hertz input?
Yeah, 50 Hz input.
For what?
Yeah, they mentioned the 50 Hz. Can you see the question, please?
Oh.
Connect to this one? I also typed the questions on our box. So it is, can an ADC with 20 bits ENOB be tested with 50 Hertz input frequency? And which AWG do you recommend us for this situation?
Oh, it's for the ADC. So, Ivan, can you see the question?
Yeah, I see the question. One moment. Of course, you can test a 20 bits ADC converter, but an ENAP of 20 bits is quite good performance, so that may be very challenging to meet the specifications.
Oh, sorry, I need a translator. 这个是可以测量的，但是对于20比特的 ENOB 的话，这个对于使用的 AWG 的一个配置的话，是有一个很大的挑战。Okay, yes.
I need more about the specifications to say something about the possibility to test this ADC.
我们需要更多的有关于这个 ADC 的相关的一些参数，然后来了解到是否这个测试是否能进行，并且使用哪一款 AWG。这个回答您觉得可以吗？
好的，谢谢。那也欢迎我们的这位观众呢，可以下来联系我们的同事，然后我们一起下来讨论具体的这个情况。那下一个问题呢是 ADC 测试如何兼顾高精度和高速率
？Test ADC, how to make the high accuracy and high speed, these two areas.
ADC and testing high speed.
So if you test the ADC, how can you just to do the high speed and also high accuracy? How you can make it?
Okay. It depends on, of course, what you mean with high speed and what you mean with high accuracy. But the most common way to do that is using the AWG 22 for the high accuracy and the AWG 18 for the high speed.
对于您的问题，对于测试这个 ADC 的话，如果您使用，当然这个高速率和高精度指的是您需要多高的速率，还有多高的精度。您可以使用 AWG 22去使用它的高精度这个功能，然后可以使用AWG 18去使用它的高速率功能。请问这个回答可以解释您的问题吗？
好的，谢谢。那么我们下一个问题呢是使用 ATX 7006测试需要多长的时间呢
？They ask, use the ATX to make a test. It need how long time?
To set up a test?
这个测试指的是配试这个测试，还是因为 ATX 的话，这也就是说您要做哪一种测试？不同的测试的话，所使用的时间应该是不同的。这个回答是来自于我的，因为我使用过 ATX。 So I help to answer some part because they know the mission exactly which kind of the test. So I just answer which kind of test they want to do.
Yeah. Are you talking about test time or to make a test for a device in the test?
They say test time.
Test time. The test time heavily depends on the conversion speed of your converter, of your ADC or DA converter you are testing. That determines the test time. So the limitation in the test time, the time it takes to run a test, is limited by your device under test.
刚刚我们工程师回答，这个测试的时间也基于您使用的，如果您使用测试 ADC 或 DAC， 它的一个传输速率，以及它所要你要收集多少的数据。请问？So they make the question more clear. So the customer want to ask, you use this one to do the configuration of the test, and until you get the test result, it's generally take how long times, and also compare with the the traditional test way. 请问您说的这个传统测试方式是指？
Het is om een ATX op te zetten.
So they say compare with use the multiple device, make the test, it need how long times, instead of use the ATX to do the configuration and get the result.
That is a very good question. With the ATX, you can do it with an easy device within a few hours till a few days. And with the traditional setup, it may take you a lot of more effort because you have to make your own software to configure the modules, to find the modules, and to synchronize every module. So that the traditional way with PXI chassis takes a lot of time, and with the ATX, can take hours till days, depending on what you need to develop. If you need to develop a load board, for example, where the device is placed on, then you need, of course, to make a basic load board. That may take a little bit more time. But still, compared to the traditional setup, it is much more faster to do it with an ATX.
所以刚刚工程师回答，如果使用传统的测试方式的话，所有的仪器设备的配置的话，都需要您自主的去产生一个软件系统去控制它们，并且这些测试的话会使用非常长的时间。但是如果你使用 ATX 的话，当然基于您所要做的测试，可以说是以小时单位来说，或是以天的单位来说。这是刚刚工程师的回答，请问这个答案是否清晰呢？
好的，谢谢。那么我们下一个问题呢是最大采样速度能达到多少
？What's the maximum sample frequency?
The maximum sample frequency with the AWG 18 is 300 megasamples. The maximum sample frequency with the AWG 22 is 2 megasamples. And with the digital I/O module, you can capture up to 200 megasamples per second. Or generate a signal with up to 200 megasamples. So the digital I/O module is maximum 200 megasamples.
OK，如果您使用AWG 18，它的采样率可以达到300兆。如果使用 AWG 22的话，它的采样率是2兆。如果使用数字接口系统的话，它的采用率可以达到200兆每秒。这个回答能否解决您的问题呢？
好的，好的，谢谢您的回复。下一个问题是，这个设备有上位机吗？支持什么系统？
你能解释一下什么是上位机吗？
呃，
ADC 的测试的，需要我调出那个图片吗？
可以的。如果您能，对，您可以直接打开那个页面。
The customer asked about the page, the microcontroller test about ADC. Do you remember the day I asked you yesterday? Can you show that slide?
I think then we have to switch back to Horst. He has a slide.
Okay.
They have one is about a microcontroller because they want to know how you test it. It's not this one.
Okay.
The user cases.
This one.
Yeah, and they want to know how you can test the microcontroller, the ADC with the microcontroller.
What they do is they apply the analog signal from the AWG to the input of the MCU. They capture the digital data either or in the MCU, or they have a digital interface that is connected to the digital I/O module.
But the ADC is in the microcontroller, so is they have the wave generation from the ATX and the signal give to the ADC, right? Because they probably have some like interface.
Yeah, it depends. It depends on the MCU. So that depends on how the MCU can be connected to the digital I/O module.
刚刚我们工程师回答，这个里面的话，这个microcontroller 的话，这个单片机的话，它是可能是可以与这个我们 ATX 里面的DIO 这个模块相连的，以进行一个数据的发送和采集系统。然后这个信号源的话，取决于您是使用这个 ATX 去输入这个信号源到这个板，还是说用其他的方式？就是这个问题的话，看具体的情况，具体的话解释，但是它是可以完成的。
好的，
请问这可以回答
谢谢
这个问题吗？
可以的。那我们具体的情况。Yeah, I'm sorry, but 我们现场的观众呢也是特别的热情哈。我们这边还有最后的一个问题，我先把它发到聊天框。所以是多久要校准一次设备呢？可以在国内完成校准吗
Customer is very exciting, so they have another question. So they asked about need how long time to calibration, one time for the ATX, and can you do that in China?
That's a good question. The calibration interval consists of two parts. You have a calibration, an automatic calibration that can be run by yourself from ATView. I can show you.
它有两个这个校准的方式，一种是一种自动校准，自动校准的话，您可以自己完成。然后现在工程师给你展现一个这个自动校准的一个界面。
As you can see in my screen, the auto calibration can be run from ATView and should be done every 3 months. At least that is recommended for the best performance.
OK， 您可以如这个界面所示，您可以每3个月做一次自助校准，这是我们公司对您的建议。And then
the second calibration should be done yearly, and that is measuring the reference voltage that's on the connector of the reference module outside. And for that, you need a very accurate voltmeter.
第二种校准的话是需要一个额外的 一个电源输入的，然后该电源输入的话是一个非常精确的电源输入，这样的校准的话是每年一次校准。And then
we recommend to perform every year a full system check at our site so that we can do a full system check and also update your software, hardware and firmware every year.
然后我们工程师是建议，最好的话是，每年是进行一次这样的全面的一个校准的，同时也可以为整个系统的话提供软件升级，对，这个能回答您的问题吗？
好的，好的，谢谢。那以上呢就是我们今天所有的问题了。然后非常感谢我们Silent的几位同事的参与，谢谢大家。
You'll come to hear.
You're welcome. Any more questions can always be sent by email to us.
如果有更多的问题的话，我们非常欢迎您可以传送你的问题给我们写邮件。对。
Okay, thank you, thank you. 现在应该我们这个直播间已经结束了，就是已经到了下一个环节了。
我们现在要做的是。
Okay, we're leaving.
Yeah. 我们可以离开。
Yeah, thank you. Thank you for this.
好的，非常感谢 host 和伊万的分享。那也感谢我们的同事嘉义以及 Silent 的翻译同事天如。那非常感谢4位给我们带来这样一个 Q&A 环节他很详细为我们解答刚才提出的一些问题。当然有一些问题可能涉及到具体的产品和配置，我们在现场没办法做出非常精确的回答。那如果有兴趣的话呢，请刚才提问的观众与我们的助教老师联系，那我们的助教老师会详细为大家解答相关的问题，并邀请我们的工程师加群来沟通。好的，那非常感谢。那针对刚才Silent的演讲以及他的一个 demo 演示呢，我们简单做一下总结。两位工程师 host 伊万为我们详细介绍了 ATX 7006A 这一套 ADC 和 DAC 测试集成系统的一个硬件组成以及软件功能，并且呢用详细的案例为我们做了说明，带来了实际的 ADC 的测试演示，让我们明白如何去使用这个产品以及如何测试 ADC， 细节而生动。那 ATX 7006A 集成系统作为行业内领先的这样一套测试设备呢，它集成了多种的测试功能，也能够全面评估 ADC 与 DAC 的性能测试。那相关的资料，我们的社群和评论区呢已经有发送相关的一些材料了，也欢迎大家下载查阅。好的，那让我们再次感谢 host 伊万、嘉义和天如。那接下来呢，让我们进行今天的第3场分享。那第3场分享呢，我们非常荣幸的邀请到了来自于德国测试测量领域知名的企业，那也是我们德斯特战略合作伙伴 Spectrum。Spectrum 成立于1989年，致力于开发和生产用于信号捕获和信号生成的超高速分辨率 PC 产品。那 Greg 他作为 Spectrum 在亚洲的业务经理，拥有应用物理学的背景，在电子测试测量领域也拥有超过35年的工作经验。不好意思，35年的工作经验，那他也专注于提供模拟和数字信号的采集以及波形生成的一些相关产品，对这个行业的应用是认知非常深刻的。那今天 Greg 将会结合他的应用案例以及他在工作中遇到的一些问题，为我们介绍如何使用数字化仪和 AWG 进行元件测试以及混合信号测试，包括测试流程、测试参数设置以及测试结果的分析和测试结果的捕获等等。那让我们热烈欢迎 Greg 为我们带来分享数字化仪和 AWG 在元件测试以及混合信号测试中的应用。好，让我们稍。
Welcome to Spectrum. My name is Greg Tate. and I'm the business manager for Spectrum in the Asian region. It's my pleasure to provide you with a presentation to introduce our company together with our business partner T-Site. In this presentation, we will take a look at how Spectrum instrumentation products, such as our digitizers and arbitrary waveform generators, can be used in different applications that involve component and mixed signal testing. After the presentation, we'll be joined by Oliver Rovini, our Chief Technical Officer, and there'll be a chance for you to ask questions. Let's just take a quick look at the topics we will cover today. Firstly, I will provide some background on the company and its major product lines. Then I will go into some applications to show how these products can be used for testing different types of components. And of course, along the way, we'll highlight the advantages that Spectrum products bring in terms of measurement, speed, and precision, and what software choices are available. At Spectrum, we are specialists in high-speed PC-based test and measurement instrumentation. That includes digitizers, which are devices that can capture almost any type of electronic signal and convert it into digital data by using fast analog to digital converter technology. We also have AWGs, or arbitrary waveform generators, that do the reverse. They take digital data and convert it into analog signals using digital to analog converter technology. Then we have some digital I/O products that can be used to both acquire and generate a variety of digital electronic signals. If you look at our product catalogue or you visit our website, you'll find that we have more than 200 different products to choose from. These come in a few different form factors. We have PCIe cards that can be plugged directly into PC systems. We have PXIe modules that can be installed in a suitable PXIe chassis. And then we have LXI instruments that use Ethernet for easy remote control and direct connection to PCs or networks. You can see an example of a PCIe card sitting on the right-hand side, and then a PXIe module, and then below that one of our LXI instruments. The company is headquartered in Hamburg in Germany and was founded in 1989, so we have been in operation for almost 35 years. Subsequently, the company's built up a lot of expertise and technical experience when it comes to PC instrumentation and automated test and measurement. If you'd like to explore the complete product lineup, the link below will allow you to download our 2024 product catalogue. Let's take a look at the digitizer technology that we offer. There are over 120 different digitizer products to choose from, with maximum sampling rates from 5 megasample per second up to 10 gigasample per second. These products have bandwidths that range from 2.5 megahertz up to 4.7 gigahertz, and they all feature scope-like front ends with programmable gain and offset. If you look to the right, you'll see a simplified block diagram of a typical input stage, and you can see that prior to the signal reaching the ADC, it can be scaled and filtered by calibrated components to maximize the overall dynamic range and measurement accuracy. There are models available with different ADC resolutions that range from 8 to 16 bits, and they all have extremely large onboard memories. For example, our top-of-the-line models can sample at up to 10 gigasample per second and store as much as 8 gigasamples of data. That allows you to make a voltage measurement every 100 picoseconds and store nearly a second of information in one single shot. Of course, you can also use the memory in other ways. You can partition it for multiple acquisitions or even stream the data in a FIFO mode for storage or processing directly in a PC system. When it comes to data transfer, we can have some of the fastest products on the market, with some achieving speeds up to 12.8 gigabytes per second over the PCI Express bus. That makes them ideal for applications like data logging or situations where you need to perform very fast signal processing. We offer cards with modules from 1 to 8 channels, and they can also be connected together to build larger systems with tens or even hundreds of channels. In automated testing applications, these products can be used to replace a variety of conventional instruments, such as oscilloscopes, spectrum analyzers, time interval analyzers, multimeters, data loggers, etc. It's a similar story for the AWGs. They offer output rates from 40 megasample per second to 1.2 gigasample per second, and bandwidths from 20 up to 600 megahertz. With 16-bit resolution, you're ensured of wide dynamic range and excellent precision. The AWGs also have large onboard memories that can be used in a variety of ways to produce long, complex waveforms, bursts and pulses, and even multi-tone signals. Like the digitizers, these units have ultra-fast data transfer speeds, and models are available with from 1 to 8 channels. In automated testing systems, you can use the AWGs to replace signal generators, pattern generators, pulse generators, RF generators, etc. To the right, you can see a simplified block diagram of a basic AWG channel. Next, we have the digital I/O products, which can be used for logic analysis and pattern generation. Designed specifically for digital signals, these instruments can run at clock rates up to 720 megahertz for acquisition and 125 megahertz for generation. Single cards can have up to 32 channels per card, and you can build systems with up to 512 digital channels. They also have large memories and fast data transfer. There's support for single-ended and differential signals with interface standards supported such as LVDS, PECL, ECL, and other differential signals. At this point, it's worth considering the advantages of this type of PC-based technology. For a start, it makes for much easier test system automation, customization, and integration. The Spectrum products are small, low power, and fully programmable. They typically offer higher resolution and allow more precise measurements than conventional test instruments. That allows more precise, low noise measurements. In general, higher resolution gives you better signal-to-noise ratio, spurious-free dynamic range, and better distortion properties. Moving the data into the PC at high speed also allows for faster measurements and analysis. For example, FIFO streaming lets you send the data directly to the CPU or GPU for intensive signal processing applications. On the top right, you can see how all of the different PCIe cards from Spectrum can send data directly to a CUDA-based GPU where it can be processed on the fly. I'll talk more about that GPU processing later in the presentation. Another key feature is the ability to build large multi-channel systems, and on the right-hand side, you can see our Star Hub option that allows multiple cards to share a common clock and trigger. With Star Hub installed, you can easily create systems with tens or even hundreds of fully synchronized channels. One trigger signal can start an acquisition or generation on all the channels, which are then sampled at exactly the same time. Okay, let's look at a few test applications. We'll start with one of the simplest semiconductor devices, the diode. In this setup, we can use an AWG and a digitizer together in a stimulus response type of configuration. Using a 2-channel digitizer, we can compare the input signal to the diode directly with the output signal of the diode. Note that the current through the diode is proportional to the voltage on channel 0, and the voltage across the diode is simply the voltage on channel 1 subtracted from the voltage on channel 0. The current to voltage, or IV plot, can then be made by plotting these two things against each other. Here we can see the result. The ramp signal generated by the AWG is shown in the lower middle screen. The output from the diode, which is proportional to the current, is shown directly above it. Besides that, on the right, you can see the mathematical subtraction of these two signals. This shows us the voltage across the diode. The lower right screen shows the output of the diode after it has been rescaled to read the current directly in milliamps. Finally, we can plot the current against voltage to display the IV plot. This type of measurement makes it easy to test and match diodes by verifying that they have similar IV plots. An automated system can quickly reject diodes that don't perform within predefined limits. Now let's look at a more complicated stimulus response setup that allows us to look at the quality of an analog to digital converter. AWGs are perfect tools for generating a variety of high quality signals, and Spectrum has a DDS, direct digital synthesis option that can produce very precise multi-tone signals. In this example, the AWG with DDS option is used to produce 15 discrete frequencies between 27 and 34 megahertz. The amplitude of each tone is programmed to be half the amplitude of the one it precedes. DDS, together with 16-bit resolution of the AWG, makes this type of signal generation easy, and the resulting signal, as seen on a spectrum analyzer, is shown on the right-hand side. Now let's look at the same signal when it's applied to a 500 megasample per second 14-bit ADC. This is actually the ADC that we use in our 44 5X series of digitizers. The data has been acquired and then transferred to a PC and an FFT performed to show the signal in the frequency domain. It's an excellent result that confirms that this ADC has very good linear and nonlinear properties. You can see the intermodulation components that appear are all within amplitudes well below minus 90 dB. Let's look at an even faster application. Of course, measuring faster signal frequencies requires higher sampling rates and bandwidths. On this slide, a data stream from DDR2 memory, clocked at 333 MHz, is acquired at 10 gigasamples per second using an M5i 3367 12-bit digitizer from Spectrum. The top left trace shows the stream of data, which is subsequently zoomed to show finer detail in the trace below it. On the right-hand side is the FFT of the original signal. This FFT immediately shows nulls occur at 666 MHz and multiples thereof it. Significant energy can also be seen going out way beyond 3 GHz. In this final example, let's take a look at a modern appliance that includes an embedded controller. The controller is used for a variety of tasks, including monitoring sensors, displaying information, and of course, ensuring the correct operation of the appliance. In this case, it is a refrigerator, but it could just as easily be a vehicle, an aircraft, or almost any device relying on an embedded processor and sharing data. Think Internet of Things. In this case, the system includes serial and parallel buses, ADCs, memory, sensors, and a variety of other electronic components. As mentioned earlier, our digital I/O cards can be used to generate or acquire digital signals. On the right-hand side, we can see how the signals of the 8-bit parallel LCD bus are acquired to show their logic state versus time. On the left, we can see how the digitizers and AWGs can complement the digital I/O cards to reveal even more information about these types of signals. For example, they can be used to observe, measure, or generate not just the logic state, but other signal characteristics such as its transition time, overshoot, undershoot, and noise level. The AWGs can even be used to replace components in the system so that you can simulate various tests under different conditions. As mentioned earlier, the Spectrum products are designed for situations where you need fast, high-precision measurements, usually in an automated fashion. To support this, the products can all transfer and stream data to and from the PC environment at ultra-fast rates. Each product is shipped with a software development kit with optimized drivers for Windows and Linux operating systems. We leverage the PCIe technology because, compared to other bus systems like USB or GPIB, it offers faster transfer times, lower latency, and scalability with multiple lanes. For storage, we can send data directly to fast RAM, SSDs, or RAID-based systems. And importantly, we support almost all modern programming languages, whether that be Python, Julia, or third-party products such as MATLAB and LabVIEW. For most Spectrum customers, measurement speed is a critical parameter, and that's why our products offer ultra-fast on-the-fly data processing. We can approach this processing in a few different ways. Firstly, for relatively simple functions on small amounts of data, we can use field programmable gate array technology. This gives you an extremely rapid result for functions like filtering, averaging, parameters, and DDS. For more intensive processing, we offer direct transfer of the data to and from GPUs with SCAP. SCAP is Spectrum's CUDA application for parallel processing. This opens the door to routines like digital down conversion, continuous gap-free averaging, filtering, and FFT processing. Importantly, the GPUs can handle very large data files, and parallel processing means the routines can be done at very high speeds. Another advantage in using a GPU is that the processing algorithms can be customized using common software languages like C or Python. So there's no need for expensive development tools that are typically required to change the firmware of FPGA devices. On the right-hand side, you can see the result of using an FPGA-based signal averaging process, where a signal which is completely buried in noise becomes quite observable after 1,000 averages. In the lower trace here, you can see the SCAP package performing on a GPU a continuous FFT and averaging the FFT result to see the information in the frequency domain. For those who don't want to write their own software, we also have our own GUI, which is called SBench 6. That's the program that's been used for this presentation. SBench 6 supports all our current products. When using our digitizers, it looks a little like an oscilloscope display. It works with very large data files and can be used to stream the data directly to SSDs and HDDs. Data can also be displayed in a variety of ways, including in the frequency domain, XY mode, and with logic. The software is fully supported for products like our Digitizer Netbox when you need remote access, and there's analysis functions built in, like FFTs for spectral analysis, filtering and averaging, cursors and waveform parameter measurements. Data can be imported and exported for third-party products like MATLAB, and acquisition and replay of the data, including automatic data resorting, is possible. Included in the software is an arbitrary waveform generator front end so that you can create almost any wave shape that you can imagine. Finally, project files make it easy to store and recall specific setups and configurations that are required for particular tests. And there's a report generation facility so that you can automatically store and print out and create a report for any specific tests that have been completed. Today, around the world, we have thousands of customers and tens of thousands of products have been shipped. In China, our products are used by a number of high-profile institutions and companies, including the ones shown below. Finally, I would just like to summarise why people use Spectrum instrumentation products. To start with, we offer the widest range of products that are based on PC technology. These allow users to choose the most cost-effective solution that meets their needs for sampling rate, bandwidth, and number of channels. Our products also offer very high resolution. For example, a 16-bit digitizer delivers 256 times better resolution than an 8-bit oscilloscope. It means you have much more dynamic range with superior signal-to-noise ratio and spurious-free dynamic range. Getting the data directly into the PC allows for much faster measurements using the latest CPU and GPU technology. As these technologies move forward, you can move forward with them. System creation and integration is also easy. You can choose the most suitable product format and software. All Spectrum products have front-end panel connections for clock and trigger inputs and outputs, along with multi-purpose digital I/O lines. The products are small in size and low in power, which makes them suitable for embedding in almost all automated systems where a PC exists. We have StarHub for easy synchronization. This allows you to build fully synchronized multi-channel systems with tens to hundreds of channels when necessary. And finally, Spectrum is a high-quality manufacturer with excellent support and reliability. In fact, we back up our reliability with an industry-leading 5-year warranty for all our products. For further information, I would encourage anyone that's interested to visit the Spectrum website at www.spectruminstrumentation.com. Here you will find our technical data sheets, application notes, user stories, and a variety of support tools. Of course, if you have any questions and don't wish to ask them now, you can contact us directly or our partner T-Site, and we'll be very happy to assist you. That concludes the presentation for today. Thanks for listening, and thanks also to our partner T-Site for arranging this session. We now look forward to answering any questions that you may have.
好的，非常感谢 Greg 的精彩分享。那 Greg 呢，为我们分享了这个 Spectrum 高性能与高分辨率的数字化仪和 AWG 产品。那并且呢，也针对这些产品在二极管测试、ADC 测试等半导体测试中的应用做了一些分析和分享，并且还用了这个嵌入式控制器混合信号测试应用的这个案例来做了一下介绍。那目前呢，我们与 Spectrum 携手，已经为国内数百家领先机构和公司提供相关方案，包括华为、中科院物理研究所、美的、清华大学等等。那下来，让我们看看现场的观众提出哪些问题，让我们远程连线一下 Spectrum 的技术专家，为我们做一下解答和经验分享。好，请大家稍等一下。
Good morning, Oliver.
Yeah, good afternoon.
So hi Oliver, hi Greg. Thank you so much for the presentation. And now we have received some questions from the audience, and we will be happy to hear your insights on it. And I would like to translate them first. There's several questions, and I will translate it in both Chinese and English. So the first question is, 逻辑分析卡时间精度能到多少？阀值电平可调吗？ What is the time accuracy of the logic analysis card? Is the threshold level adjustable?
Did you want to answer that, Oliver, or should I?
Sorry, I had a call. I did not hear the question. It was overlaid. Sorry.
Yeah, I can repeat it again. So what is the time accuracy of the logic analysis card, and is the threshold level adjustable?
The threshold level is not adjustable. It's the digital input card is a LV TTL card, so it expects low voltage TTL signals with a fixed threshold. The time accuracy is just help me have a way look into the data sheet.
Well, it will depend on the model, obviously.
Yeah, but digital data acquisition, we only have the. Pardon. Yes, good question. So, what model are we talking? Are we talking about the low speed, the 75 series, or the fast speed, the 77 series?
Do you know that, Sophia? Which model are they talking about? Because we have different speed grade logic acquisition cards, and of course the faster cards will have better timing than the slower cards. So it's kind of dependent on the card, on the model. The fastest card.
So the timing accuracy is 1 ppm on that card.
So 1 part per million?
1 part per million, and the time resolution depends on the version you use and the sampling rate you select there.
So if you were running at the fastest clock rate of 700 megabit per second, then you're going to have a resolution of a little over a nanosecond, huh?
So yeah, it's 1.4 nanoseconds, yeah.
Yep. Does that answer your question, Sophia?
Yes, thank you. So our next question is, 数字化仪能直接测电流吗？电流范围和精度是多少？ So could the digitizer measure current directly, and what is the current range and accuracy?
Okay, I will answer that one. The digitizer is designed to measure voltage directly. So if you want to measure current, you're going to have to use some kind of current conversion. That could be a current probe, for example. Again, that will depend, the model of probe you use would depend on the digitizer that is in question.
Yeah, thank you. So the next question is, 什么场景的 ADC 测试会需要做这种多音信号的测试？我们一般是做单音的。So we usually use single tone and single test. In what scenarios or applications would ADC testings require multi-tone signal test?
I'm not sure I understand that question. Can you just repeat it for me, Sophia?
Yeah, so we usually use single tone and single test. And the customer is wonder what scenarios or applications would ADC testing require a multi-tone signal test?
Okay, yeah, the multi-tone test just makes it much faster to actually complete the test. Obviously, if you use single tone, you have to do separate measurements for each tone. But by using one generator that is outputting multiple tones at the same time, you can effectively make 10 or 15 or 20 measurements in one shot. So that's particularly useful for people who are wanting to look at things like the linearity of the ADC.
Thank you for your feedback.
Yep. Okay.
So next question is, 采集回来的数据点能逐点带上时间戳吗？提供的时间戳是什么形式的？ So can the data points collected be time-stamped individually? And what format is the provided time-stamped in?
Okay, maybe I'll answer that one again. Each acquisition that's made by the digitizer can have a trigger timestamp, and then of course you can have each sample point referenced to that trigger timestamp. So that should enable you to identify every point in an acquisition.
Okay, thank you for your answers. And we got a last question here. 能在 S-Bench 6配套软件中使用流式传输特性吗？可以做一个演示吗？ So is it possible to utilize the streaming feature in the S-Bench 6? And could you give us a demonstration?
The short answer is yes. And for a demonstration, I'm not sure. Oliver, do we have a video of doing streaming? It's a little bit difficult to show streaming live, huh? It's
yes, we have. So yes, showing streaming is only possible for slow speed because the display will delay the streaming process.
Yeah.
But
the short answer is that yes, S-Bench 6 does support streaming. The customer, we could potentially show a streaming example at slow speed, but for anything at very high speed, as Oliver is saying, the display of the computer will actually compromise the fast streaming rate. So you actually turn the display off while you are streaming the data.
Yeah, thank you. And in terms of the demonstration, it is okay. And we can talk directly with the audience who asked these questions and to give them more demonstrations later. So that is all the questions. Thank you so much for your answers. And I believe that your invaluable expertise and insights can give a fruitful exploration to our audience in this field. Thank you so much. Thank you, Greg and Oliver. We're very happy to have you here. Thank you.
Thank you, Sophia. So I would just add that as you have a demo unit there in China, it should be fairly easy for you to set up a demonstration for the customer using S-Bench 6 and streaming and just show him how that works. I'm sure Zeki could do that quite easily.
Yes, we can do this with the customer. Thank you. Yeah. Thank you for your suggestion. Yeah.
Okay, I would certainly like to thank T-Site for organizing the seminar. I look forward to.
好的，非常感谢刚才的 Q&A 环节。那让我们再次感谢 Greg、Oliver 以及我们的翻译同事嘉义。至此呢，我们的研讨会就进入尾声了。大家可以添加助教的微信，进入行业的技术交流群，与我们今天演讲的几位讲师近距离交流，了解更多的行业动态和前沿技术。那更能及时参与我们组织的其他精彩活动。那另外，如果大家有任何的想法和建议，也可以添加助教的微信告诉我们。那我宣布德斯特半导体测试研讨会到此圆满结束，感谢大家的支持。那后续我们还将举办车辆无线通信及测试的一些研讨会，分享车辆无线通信测试 的应用和前沿的技术与话题。那届时我们将在群内发布更新的一些活动详情，敬请期待。德斯特测试测量智库在线加油您的未来，让我们下次再见。